Well, I knew you'd be there first, Ellie. Thank you. But somebody's joining you too. Let's see who else is there. Now I got two others joining you, so they can type in and say hello, and I can see who I got here. I got Anne Sophie. And I got Zach. So 75% of my group. Let's see if I can get 100 today. Teresa, are you out there? Hope everybody else is doing well in this crazy Corona time, keeping your sanity here in the dark of winter. Although I noticed yesterday at 5 o'clock, it was still kind of almost light. So things are getting better. Light at 5 o'clock. There's hope that spring will really return someday. Okay, let's go ahead and begin, and hopefully Teresa will catch up. I think I see four of you, but somehow maybe she can't respond. I don't know. My first goal and my main goal for the hour is sort of my main goal for the hour is to see if you have some questions on the many problems I gave you. Okay, so because I don't know how much we'll be able to meet next week because I've got all these grade conferences and stuff. Okay, so have you tried any of these now on springs moving and pendulums moving and frequency and period and stuff like that? If you have, let me know if you've gotten stuck anywhere because I can help you on any you've gotten stuck on the A or B ones. Okie dokie. So think about that, look at it, and see how far you've got. If not, we'll do something entirely different, but that is really my first priority. I'll try and see if I can meet with you at least once next week, but things are pretty tight. I got MSAs Wednesday, Thursday. I got grade conferences Monday, Tuesday, and Friday. You're theoretically dismissed at 10:30. So I know it's online, but I guess we'll just probably not meet that Friday. So far, you haven't had any issues, Ellie. Yeah, go ahead and read through some of the other ones. Everybody read through and see if there's any you don't really get what they're saying, okay? I won't do them for you, but we'll give some clues out with you if you have problems. Yeah, I like the problems in this section. They're all kind of goofy. They got funny people doing funny things for the most part. The MSA, as far as I know, Anne Sophie, are in person. So we've got to go there to school, we teachers, but we're in a big room all spread out with two presenters with masks on. So I think it's pretty safe because nobody else will be in school. But I think they're in person. The grade conferences will all be online. We'll be doing Google Meets for the first time ever. Any other questions from you? How are you all doing okay at home with your AP and non-AP classes and all the stresses of online learning? Zach, far as I know, our clausur will be in school because I've never given an online clausur in my life, and I'm not sure legally we can even do it. So stay tuned, Zach, because we don't know when we'll all get inoculated and what the Senate, in all its wisdom, will decide. But for right now, the clausurs will be in person. And I think we got a ways to go. I got to look at the schedule, but I think it's going to be a while for us because I have you guys until the end of the regular school year. So it's stressful, but you're dealing with it. Good. I am too. I don't like it as much because I like seeing all of you face to face. It's a lot more fun for me. But, we do what we got to do, right? And my main thing is just for us to learn some physics and maybe we can have some, virtual fun doing it. And let's see. Mm. And Sophie, do you feel like you're sick of being home? I'm sick of being in this basement, I'll tell you that. Okay, if you're doing all right on these problems, then we're going to do something different, okay? Something physicsy. Yes and no. Oh, great. Okay, so let me write down. We'll know Teresa. Teresa, if you're there but can't respond, maybe write us a text in the total physics chat. Okay, what I want to talk to you about is what we're going to study the next bit. Ooh, I got another comment or two. Hold on. Yeah, I don't know, Ellie. It's not really tiring. It's unsatisfying. Unsatisfying because I don't know if you're laughing at my bad jokes or not. Okay. And I don't know if students really understand or not. That's really the more important thing. I don't really care about my jokes. Okay, so let's talk about what we're going to deal with the next few weeks and months. All right. We're going to talk about light and sound in various aspects. And of course, light and sound both travel in good. Thank you. Both travel in waves. So I want to talk to you with a real basic idea today of what waves are and what the two main types of waves are. Now, I had a little something I brought from school, and I cannot find it anywhere. So I will do what I can to try and show you the two types. Okay, so here we go. Let's talk about waves. This is sort of after the harmonic motion chapter in your book, but really it's a combination of things we just need as a basis. Okay? Waves are, well, what kind of waves? What kind of waves? Sound and light, but where else do you guys experience waves? Firsthand, you've experienced waves. Whereabouts? Very good. Yeah. Good. Oceans, lakes, ponds, wherever. So water waves are a good example of one of the types that we have. The beach, exactly, Zach. Right. Good. So of the all waves are nature's way. I could spell nature. Nature's way of transmitting. Well, let's see if you can fill in the blank. Waves are nature's way of transmitting. What do you think? No, probably not frequency. The answer here would work for all types of waves, by the way. Light waves, sound waves, and Zach has it. Thank you. Energy. And it can't be mass because light waves, like, well, you can say they have mass under one theory, and the other theory says they really don't. So, and really, sound waves don't really have mass as such either. Okay, but all waves transmit energy. Take an imaginary pond here. Ready? and I'm going to throw an imaginary coin in my pond. Here comes the coin. Ready? Okay, so the coin drops in the water, and think of what it's going to look like. It's going to be circles, right? You've all seen this, and the circles move out, don't they? The circles move out from the disturbance. So when I create a disturbance, I've like made some energy to do that. Well, I've used some energy to create the disturbance. I've dropped a rock or whatever in this water. And then that energy from the disturbance goes out and out and out away from the source of the disturbance. Really, all that I like that word disturbance. Maybe I'll say this here. It's nature's way of transmitting energy out from a disturbance. And I like that word disturbance. It could be a pebble in the water. It could be a sound that disturbs the air. It could be light that disturbs the universe by traveling through it. There's all sorts of disturbances. Yeah, like skipping a rock, exactly. That if I skip it, I'd get a number of disturbances, wouldn't I? So I'd create a lot of different waves. Ute, let's talk about the two types of waves. And the two types of waves, well, the first type we'll talk about is called a transverse wave. That's the kind you guys are probably most familiar with. Transverse waves. I don't know if this is going to work, but I'm going to get the little spring I had yesterday and see if I can try something, okay? Heaven, yeah, help me here. I wish I could find the other thing I brought, but I can't put my finger on it. Okay, here we go. So I look at a wave sideways. I'll try and do this against the whiteboard. So I can make it like this shape, can't I? I gotta bend this, but I can make it, and I can send the disturbance through the wave, or send the wave disturbance through the spring. So I've got like, okay, so it goes up and down. That did not work very well at all. Let's just have you imagine a water wave, right? It's one of them, man-made. Well, yeah, a lot of them, like if sounds are man-made or animal-made or whatever. Okay, a transverse wave looks like this. Think of like the wave we know from the water. Why not? I'm trying to make it the same throughout, and I'm not doing a great job, but not too bad. So try and draw yourself a wave that stays looking the same throughout, okay? All right. So as a transverse wave, example is, of course, water. Do you know what else travels in this sort of wave? Do you have any fun guesses? What else would travel in this kind of wave, aside from water? Good, sine cosine graph. Yeah, nice. Sound, no, that'll be the other type. But it ends up being a sine cosine type curve, yes. Light. All the different types of light we have follow a transverse wave. Okay, let's get some parts of these waves. All right, so here we go. Exactly. Okay, what's the top of a wave called, or the bottom? If you've ever been sailing and stuff, you might know this anyway. The top of a wave is called a what, and what's the bottom of a wave called? If you know either word, type it in. So parts of a wave, the and the of a wave. And I'm going to label them as you tell me. Good. All right, Ellie. The trough. That's one that a lot of people don't know. So here's how you spell trough. Trough. A typical weird English word. A trough is also something that horses drink out of, right? Right? Okay, so there's your trough here in the wave. That's how I remember it. Can a horse drink out of it? Then it's a trough. Good. And the tops are called, thank you, Ellie, a crest, as did Zach, knew that too. So the top is called a crest. Nice. Super. Okay, then there's this distance that I'm going to draw an imaginary line here through the middle of this sucker. Oh boy, I hope I can do this well. That's not too bad. Well, that's pretty awful. Okay, well, I think I got to fix my wave out here. That's pretty bad. It should be right through the middle. Anyway, sorry about that. Okay, so this distance, see if you know what it's called. The distance from a midpoint in the wave, kind of like the equilibrium position we talked about with harmonic motion. So that distance from there to the top, and ideally it's the same from there to the bottom as well, if I'd drawn my waves better, okay? But what's that distance called? It's got a special name that starts with an A. The of a wave. Oh man, we got it already. Some of you know, and Sophia and Ellie know both of them. Super. It is. It's called the amplitude of a wave. So if you got some really big waves, they might be big because they've got a big amplitude. Dynamite. Then, what about the distance? Let's say I go from, let's do the green here. Let's say I go from crest to crest. If I do, it's called the what of a wave. What is crest to crest called? By the way, I could also go trough to trough. It doesn't really matter. Or I could go middle to middle, but it should be the same distance each time. What's that called in a wave? Yeah, super. Thank you very much, Ellie and Sophie. You've had this before. So that's called a wavelength. And the symbol is a funny symbol. I'm going to try and draw it big. It's the Greek letter lambda. Like that. That's the symbol of wavelength. Okay? And there it is down here. So this is a wavelength as well. Yeah. And it's lambda. I think. I think there's a B in there. No, I think there's not a B in there. Sorry. Just joking. So I think it's ALMDA. If you know I'm wrong, let me know, but I think that's lambda. So no lamb and lambda. Okay, good. Right. Let's see if you got other comments before I ask you something. Last year's physics and pre-calc. Super. And you guys have had some of this. That's great. Okay, now, the next thing you may not have had, because I'd be surprised if it's emphasized in pre-calc, but let's find out. I got to erase a little bit of the top here so I have something to work with. Okay, the is the stuff or material, sorry, better word, material, a wave travels through. So what's that word? What is the name of the stuff that a wave travels through? Sorry. Oh, well, that's okay. All right. It is lambda, really? There's really a B in there? God, I never remember that. And I taught this like 1,000 years. All right. Thank you, Anne Sophie. I really never remembered that this would be. It's really a lambda, huh? How about that? Thank you. Okay, so what's the name of the stuff? It starts with an M. Yeah, Ellie, thank you. It's a medium. Now, it doesn't mean small, medium, large. Medium would be, let's do some examples. Well, of course, I could have water waves, so water would be a medium. What could be another medium? What else could waves go through? Give me some other mediums. There's several. What else could waves go through aside from water? Good. Yeah, air. Sound waves and even light waves can go through air. Air's a good medium. How about something on the outside edge of a house? We're going to do a study of this if I ever see you again. Glass is a medium as well. Concrete is a medium. I can feel waves through concrete sometimes if they're like an earthquake or a vibration. Yeah, now you're thinking. Any others you guys come up with? Carpet or wood, sure, but really any substance, of course, right? Good. Turns out one wave doesn't need a medium, and that is light. So it can also be a vacuum for some materials. No, not for, okay, for light. I better put that in there. So vacuum can be the medium for light only. All right. Ute. Well, why am I bringing this up? Because I've got to have you imagine that you're a duck. Okay, where am I going to draw you? I'm going to draw you down here. So here you are. You are a duck. There's your little legs. Here's your neck and your bill. And there's your little wings. That's one of my better ducks. As the wave goes this way, I know my drawings getting kind of busy. The wave goes this way, let's say. So that's called the wave direction. What's the duck do? You are the duck. What is your motion if the wave is going this way? You're in the water. The wave is going this way. What is your motion? And let's pretend it's got lots and lots of crests and troughs going this way. How will the duck move? Yes, exactly. It'll move up and down. And I don't know what you mean by circularly. I think it's just going like in a line. It just goes like that. So if you're a duck, you're going to rise up as the crest comes by. And as the trough goes by, you're in a hole. Then you rise up and you go down, up and down, and up and down, and up and down. So here's why I'm saying this. For transverse waves, so I'll put a little arrow up here, wherever you can write this in about transverse waves. The wave direction and medium direction are perpendicular. In other words, the duck is going up and down, but the wave is going this way, wave direction. So they are definitely at 90 degrees to each other. So it's this sort of sense, up, down, but waves moving this way, okay? So 90 degrees. And that distinguishes a transverse wave. Transverse means across. So it's going across the medium. Now the water's not moving, otherwise the duck would be going slamming into shore, okay? So the medium does not move, but the wave goes through the medium. It's the same with light. The light is coming through the air, but the air is not traveling with the light and hitting you, okay? Just the light is moving through the air, okay? So that's what's up with a transverse wave, our first type of wave. Yeah, so the duck is representing the medium, okay? I should have said that. Thanks, Ellie. So think of the waters just going up and down, and to help imagine that, I imagine you're the duck. So the medium is going up and down with the duck riding on it, and the waves going, let's say, this way. Huge. Hey. Okay. Any other questions on that? That's our first type of wave. And because it's light, it's really, really important. Okay. Let's do another type of wave, unless we got another question. I guess we're okay. All right, so here we go. Caramba, I'm losing all my stuff here. All right, including what I need next. Okay, so the other type of wave, and I'm ashamed to say I didn't bring the right tool, is this sort of wave. Yes, longitudinal, and we're going to use another name for that, but it's also called longitudinal. And Sophie, that's right. Give this a little push. And if I give it a push, the push kind of goes through. It looks like this, and it keeps going through the wave, that push. And it's called a compression. I'm going to artificially hold that. So if I do this, and I'm sorry I didn't bring a bigger wave to do it, a bigger, like, slinky is what I wanted. But if I do this, and I'll try and remember this to show you next week, I can make a series of compressions. So I can make a squishing, and then the squishing business goes through the wave. Squish, 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 squish. And behind it is the opposite. They're a little more pulled apart, the parts of the wave. And then comes the next compression. Squish, 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 squish. And the squishiness goes through the wave. It comes out the other side. Okay? So that compression goes through the wave, and I'll tell you what the opposite is called as well. So let's draw that and name it. So the second type of wave is called a compressional wave, because we give compressions to make it. And the other name, as Anne-Sophie knows, is called longitudinal. So compressional waves. So let's draw this one that I just did, but in bigger. So let's say we got a series of compressions. So we're going to go and say, and then close together. Okay. Well, I could have drawn that better, but I guess you get the point. So this is a compression. Here, I'll label this. This and this. They're supposed to be tighter together, like I pushed them together here. Okay. Supposed to be like that. So those are my compressions. So I got two compressions, one here and one here. And when they're more pulled apart, So between the compressions, that's got a funny name. And so from like here to here, it's called a rarefaction. And here's another one over here, okay, out past the other compression. So I got another rarefaction. It looks like it should be it's a fraction, but it's not. It's just rarefaction. Yeah, okay. So I got rarefactions and compressions. I can still have a wavelength, can't I? So let's use maybe green, and I'll go and make a wavelength. So the wavelength could be from like the middle of the compression here to the middle of the compression here. And I'm going to do our new symbol with that. So there's lambda, my wavelength. Or I could do middle of a rarefaction. So the middle of a rarefaction, it should be the same distance, okay? Maybe I could do that too for grams. And lambda. And you could just about guess one compression and one rarefaction would be one cycle, kind of like we talked about with harmonic motion. So I have several cycles that would probably go through a little spring like this if I kept making compressions. Several cycles. Similarly with the transverse wave, one cycle would be like one crest going through the duct. So the duct could have a cycle going through it every time it's going a down and up trip in the water. That would be one cycle going through the duct. Okay, now, let's talk about the medium. So let's say this is the wave direction. Wave direction. What direction does the medium go in a compressional wave? So the wave direction, let's say it's still going this way in this picture. What direction does the medium go in a compressional wave? The stuff it's made of. Remember, in the other wave, the duct went up and down. The medium went up and down. What's the medium do in a compressional wave? Yeah, the same direction as, I assume you mean, as the wave. Yeah, so it also will be parallel to the wave. And it pretty much goes back and forth. So this would be the medium direction. So the little coils of the spring go back and forth as the compressions go through. So that's kind of what's up with a compressional wave. Hey, wherever I can write this, a compressional waves. Oh, where can I write this? I gotta erase the top, I think, and write it up here. I just don't have any room. So, hey, in compressional waves, let's abbreviate that to COMPR. The wave direction, or let's just say wave and medium directions are the same. Or you could say they're parallel if you want. Doesn't really matter. So they both are kind of going back and forth, or if the wave is going one way, the medium goes back and forth They're in the same axis, we could say. That's a nice math way to say it. Same axis. They are not perpendicular. Ute. Good. And shame on me. I didn't do what I wanted to right away. I got to erase a little bit and put a little something down here. I know you can't do this, but you got more paper than I have, whiteboard probably. So let's talk about some examples. Well, we did a spring, okay, in a spring. But what are some other examples? Yeah, exactly. Thanks, you too. What are some other examples of stuff that moves in a compressional wave? So a spring, anything else you could think of? Yeah, right, exactly, Anne-Sophie. This time it is sound. Anything else you can think of? There's a couple things. One you probably haven't experienced, but one you have. Let's see if somebody can come up with it. Let me give you the one that you haven't experienced, I hope. And it's some types of earthquake waves. They go through the earth as a compression, okay? So the earth can be a medium too. Some earthquake waves. Now, earthquakes make 3 different waves. So they're not all compressional waves, but some of them are. The ones we're most familiar with are the compressional ones, the S&P waves. Anything else you can think of? Vibrations. Have you ever been standing on a street and somebody goes by in a car and they got the bass really turned up? Can't you feel it going right through you? Those vibrations can go right through the either air or right through the ground, and those vibrations go right into you through your body, and you feel that in your body. Yes, and when you play an instrument, you can feel those same vibrations in the instrument. Exactly, and so especially if you're playing like flute or something, you can feel the wave coming into your body as a vibration. Mm-hmm. Another time you've experienced it probably is Sylvester. Okay, if you have a lot of fireworks, some of them are so loud that explosion as it comes towards you is also a compressional wave. Okay, whether it comes through the ground or through the air. So you've experienced vibrations quite a bit. Yeah, cool. Any other questions before we go on here? We get a little bit more done. Okay, so those are the 2 types of waves and examples, and their difference is in terms of which way the medium's going. Ute. Good. Recall. To get velocity, if we assume something's moving at a constant velocity, pardon me, I divide the h by the h. So how do I get a constant velocity calculated? Divide the h by the h. You'll see why I'm asking. Yes, I know you know this. The h by the h. What's velocity? I should write the word out. Over h. Thank you. Good. All right. Both of you right at once. So distance over the time, or or change in distance over change in time. Super. Let's talk about this for waves. It's really similar, okay? To get the velocity, I don't take the distance. What do I take? Look back at your drawings of waves. What do you suppose I'll take instead of distance about a wave? What'll be on top there instead of distance? Thank you, Elliot. The wavelength. So that's a distance too. And we do wavelengths, by the way, in meters, just like we do other lengths. So it's not a big difference. So wavelength. All right, now this one's a little tricky. The time. What's the time called for one cycle to go through? Because a wavelength is basically one cycle. What's the time called for one cycle to go through something? Nice. Oh, you guys are sharp today. Yeah. Elliot, answer for you right away. So it's the period. So essentially, here's my equation in letters. The velocity equals the lambda divided by the period, which was a capital T. And that's sometimes useful, but recall that T was equal to 1 over something called the frequency, or 1 over F. So therefore, if I substitute this in, or another way to say it is F equals 1 over the period, and that's what you're going to use in some of your harmonic motion problems. So check out what happens. Oh, look at this. Oh, I got 1 over T right here. So the equation becomes V equals lambda times the frequency. And that, my friends, is a really big, important equation. Put a box around it. It's called the wave equation. Now, here's a disclaimer. My disclaimer is, okay, if you go to a physics text, especially a college physics test, for frequency, often they don't use F. They use this letter. Nu is used. And nu looks like this. And I'm going to put this in parentheses. Can you guess why I use F instead of this letter? What does that look like? What does that letter look like? Here, let's kind of in the glare. Why do you suppose I don't like that letter much? Yeah, it looks like a velocity. So I don't like nu. I'm unhappy that people picked that long ago. So I think of this equation. Okay, if you got to use nu here, okay, someday you'll get used to that. But for you and I, we're going to use F for frequency. So the velocity equals the wavelength times the frequency. It's a beautiful equation, really, really super, super useful. Okay? Yippee skippy. That is a great place to stop on a Friday. I will look up my schedule, and by Sunday, I'll tell you when we're meeting. And I don't know how often it'll be next week, to be really honest. Okay? But I'd like to meet with you at least once more to see if you got questions on the problems so far. All right? Okay, be well. Have a great weekend. Stay healthy. And I don't know, go out and enjoy the rain? No, maybe sun if we get some. Okay, bye-bye.